Alrighty, welcome to Chapter 19 Physics video. This one's going to be all about interference and diffraction, which is going to finish up our unit on light. Before this, you saw how light could behave as a ray reflecting off of mirrors or traveling through and bending when it goes through materials, called refraction. And so now we're going to see what happens when we consider the wave-like nature of light instead of the particle-like nature of light. The first thing we're going to do is watch a cool video that I found online, since I can't really do a demo here in my living room. I'll show you.
Light waves. We use the phrase all the time, yet very rarely do we ever see any phenomenon that really exposes the wave nature of light. Now this demonstration is designed to do exactly that. It's really simple to set up, yet it's profoundly surprising. The first part of the experiment is a laser. I'm using green because the eye is most sensitive to green light, so it's really easy to see in a classroom. I'm using a laser pointer to make sure that it's eye safe, and I've arranged it so that if I twist it in the clamp, I can get the laser to come on and hold itself on. And now I'm going to shine the laser onto the second part of the experiment, that's the screen. You can see the path of the laser beam by just using a piece of paper. You can track the laser beam back towards the laser pointer, give it that James Bond effect. Now the third part of the experiment is simply a thin piece of wire. Now, if I slide my finger up the wire, you should be able to consist of sliding the wire into the path of the laser beam. We then look on the screen to see what's happening. Now, before doing this, I like to ask people what they would expect to see on the screen. And normally, perfectly reasonable.
Okay, I will pause it so that you can think about what you think will happen. So take a few seconds and ponder what you think would happen, and then resume, or then pause the video if you want, and then keep watching.
They tell me they'd expect the spot to be obscured by the shadow of the wire. So if this is the spot, they'd expect the wire to move in front of it, something like that. So that on the screen, we'd see a dark line down the center of the spot. But in fact, that's not what we see. Let's take a look at what actually happens. So I'm going to slide the wire across, and you need to be quite careful to get it. There we go. You should just be able to see here where the laser is shining over the wire. And on the screen, oh wow. If you look at the spot, you should be able to see that there's no dark line down it at all. It's still perfectly bright. But on either side of it, you can see bright and dark bands extending out many times the diameter of the wire or the laser beam. So the question is, how do we relate this pattern to the wave nature of light? Well, light waves travel from the laser over to the wire, and they diffract around each side of the wire. That is, they're bent to fill the space beyond and behind the wire, extending over to the screen. So in this region, we observe interference between the light waves that have come around one side of the wire and around the other. Where the waves are in phase, that is, where the crest of one wave matches the crest of a wave that's come around the other side of the wire, we observe constructive interference. And that's what leads to these bright regions on the screen. And it's what explains the absence of a shadow in the center. In this region, we've got constructive interference from light which has traveled around each side of the wire, because this point is exactly equidistant from either side of the wire. We also observe destructive interference. That's where the light traveling around one side of the wire interferes destructively with the light that's traveled around the other side of the wire. And that's what leads to the pattern we see on the screen. Now it's easy to get lost in the maths and the geometry that explain this pattern, but that's not the point. The key point here is that it's impossible to understand this phenomenon without appreciating that light has a wave nature. And that is what makes this demonstration so important.
Pretty cool, right? Alright, so now we're going to learn the math and the geometry that he said is not important. well, it's not important to appreciate the phenomenon, but it certainly is important to be able to calculate values. And this is actually very useful in calculating the wavelength of unknown sources of light, and also to find the widths of very small, thin objects. So you could actually, he said he knew the width of that wire in the video, but you could actually use the length between the diffraction pattern bright and dark spots to work backwards and calculate the width of that wire. So if you think about measuring something that's only a few micrometers thick, you can't exactly use a ruler to do that. So using diffraction is actually a good way to measure very small distances. And hopefully we'll have a lab later on in class where you're actually going to measure the thickness of your human hairs, which you need something special to measure something that small. Okay, so let's kind of start at the beginning. He talked about a little bit of this, but we'll continue through. Interference. So what happens is when two light waves come across each other, they can interfere, and this is the same as what we learned way back in chapter 14, just with basic wave interference. When the crest and the crest match up, the wave will be even larger. So if two light waves are crossing each other's path, and the two crests line up, you'll get an even brighter spot. And if you have one crest and one trough line up with each other, they'll cancel out, and there will be no wave at all, and it'll be a dark spot. Interference is the kind of phenomenon behind this that explains it. But then also, the second thing is that this requires coherent light. And what that means is, if you think about the light waves as going like this, up and down, all of the light waves are in phase, which means all of their maximums occur at the same time and all their minimums occur at the same time. That way when another wave comes across, you have a set maximum here and a set maximum here, and you can see when they pass each other. If the waves coming in from, say, the two sides are all out of phase, then it's kind of like you have every possible phase here and every possible phase here. When they go on top of each other, you're still going to have every possible phase, and you won't actually see any interference. So you're only going to see these interference patterns if the two waves that are passing each other are coherent, which means all the ones on one side are in phase with each other, and all the ones on the other side are in phase with each other. So it's almost as if you just had a single wave here and a single wave here passing by each other. Even though in real life, of course, a laser beam or a light from a source is a lot of waves. You want them to be all in phase so that it acts as a single wave. Okay, so what that guy talked about is not a double slit interference, even though it yields a similar pattern. So this is the first one in your book, so I'm going to go in order with how the textbook went. So it's called the double slit interference, and Thomas Young is the guy who did the experiment. And let's kind of analyze what happens. So the first screen here with a single hole is simply a way to get coherent light coming through. And nowadays we use lasers to do this, but I think back then when he did this experiment they didn't necessarily have lasers, and so he had to find a way to get coherent light. So he got the coherent light by having it diffract through a single slit. Don't worry about that. Basically our experiment is starting right here. So our experiment that we're looking at is this part that I've drawn a box. So you have incoming light that's all coherent, and you have two slits, one right here and one right here. So when this wave passes through this slit, it diffracts, which means it spreads out, and these red and yellow alternating bands are representing the peaks and the troughs. So maybe red is when you have a max and a max, and then yellow is when you have a min and a min, something like that. And so you're alternating between the peaks and the troughs, back and forth, back and forth. And so you have some peak coming out from here, and then this one you have a peak coming out as well. And then as it moves forward, it'll be a trough, and then a peak, and then a trough, etc. Now, when you have some waves coming from this guy, once they start crossing the waves from this guy, you might get a peak and a peak, which will be an even darker peak. You might get a trough and a trough, which will be an even lower trough. And you might get a peak mixed with a trough, which will cancel out. So anywhere you have a red crossing a yellow, that's where you have one peak and one trough, and they cancel out. And you can see that it lines up with this one, which cancels out, and this one, which cancels out, and this one, which cancels out. So the place where the peaks and the peaks and the troughs match up, they form a linear pattern, which leads to a specific spot on the screen. And so these will always be canceled out, and so this spot on the screen will always be dark. Okay, right down the middle you have peak, and then trough and trough, peak and peak, trough and trough. So they're always at maximum amplitude, so you're going to maximum brightness here. So this is going to be bright, It doesn't even say, but I'll write it in. And then you can follow the next one. Here it's a peak and a trough every time, all the way out. And so this one is going to be dark again. Dark. And then here you've got double trough, double peak, double trough, double peak, which means it's getting the maximum amplitude. So basically, it's oscillating like this. So if you have one coming in like this, and one coming in like this, if they're in phase or they match up, then this peak will match up with this peak and give you an even bigger peak. So this would be super bright. So it took me when I was a student a little while to understand that it's not that it's bright when it's up here and it's dark when it's down here. This whole thing is oscillating back and forth very, very rapidly, which is what you perceive as regular light. So it's the amplitude from here to here that determines how bright it is, not within a single wave, a dark spot and a bright spot, a dark and then a bright. So this whole thing is a continuous bright spot, whereas a flat line would be a continuous dark spot, and something like this would be a continuous, dim spot. So that's the difference between those two. So when you're doing this kind of experiment, if you want to calculate things like where do these bright and dark spots occur? What was the distance between these two slits? What wavelength is the light that's passing through? How far away is the screen? All those different parameters can be calculated. If you measure some, you can figure out the others. So the four parameters which are going to come into play are the distance between the slits, the distance from the screen over to where the slits are, the wavelength of the light coming through, and the distance between the bands. So the distance from here, say, over to here. So the distance from here over to here. And we can calculate or derive an equation relating all of these things together. This picture here is just a second image of what's going on, showing the same thing as this one. Okay, so now I have a video to watch for this one as well. This one's pretty quick. You can see that there's a point source emitting waves, and the crests and the troughs come out, and then a second point source in a different location emitting waves with crests and troughs coming out. And then once you activate both at the same time, you can see sometimes a crest will match up with a crest, and sometimes a trough will match up with a trough, and then other times you'll have a crest and a trough. And so you can see, like, along this line here, that's when you have a crest and a trough matched up with each other. And so that's where you have a dark. And then here it's crest and trough alternating, so you'll have a bright spot, and then dark, bright, etc., all the way around. And these are going to radiate outward in all directions according to sine of the angle, and we'll do the math in just a second. Okay, so here's the slide that will allow us to do some calculations and some math. The equation that we're going to end up deriving is relating those four variables I talked about. X is going to be, X is going to be the distance from the bright spot to the bright spot. So this distance from the central bright spot out to the first bright spot is the distance x. L is the distance from the screen over to the slits. D is the distance between the slits. And of course, lambda is the wavelength. Okay. Sorry, I almost spelled wavelength wrong. So now to do this math, I'm going to derive it real quick and try to explain it. If you are not at all interested in the math here, you can skip this, but if you're taking the class for the math section, I highly recommend that you do follow along. We can draw one triangle from here up to here and down to here, and we can label this angle here theta. Okay, and we can say a second triangle here is going to go like this. And this is going to be a right angle. And this one is aimed up at this same spot here. Okay. So, we can also draw in this line here. Sorry, it's kind of messy. But essentially what we have is this small triangle right here, and this large triangle right here are, wow, that was a mistake, sorry. This small triangle here, with the right angle right here, and this large triangle right here are similar triangles. Okay, so this angle right here, we can write sine of this angle equals opposite, which is x, over hypotenuse, which let's call this h for now, opposite over hypotenuse. And then for the other triangle, we can write sine of the angle. For this little triangle right here, whatever this side is right here is going to be opposite. Here's the angle theta. Sorry, it's super messy. This side right here is going to be opposite, and this is going to be the hypotenuse. So to figure out this opposite side here, if we want a bright spot here, then the light wave that travels from here up to here should be in phase with the light wave that travels from down here all the way to up here. So the way that those two waves will be in phase, obviously this one has to travel a longer distance, right? So the extra distance that it travels is equal to this much right here. That extra distance that it travels should be exactly one wavelength, and that way they'll be in phase again. So that distance right there is going to equal one wavelength on that side right there. So that's going to be the wavelength divided by the distance between the two slits, d. Okay, and now we can make an approximation, assuming that the wall here is much farther away from the slits than the height of this distance, then this hypotenuse and this length here are almost the same. So let me draw it to scale. To scale, the bright spot is going to be like right here. So if this is our right angle, then this is our hypotenuse. And so if it's to scale, if this distance L is much, much bigger than this distance x, you can see that the hypotenuse is almost exactly equal in length to this base L. So in place of this h, we can put in L. Again, that's because of the approximation that the screen is much farther away than the length of this distance to the bright spot. And so since sine of the angle equals x over L and it also equals lambda over d, we can set those two equal to each other. X over L equals lambda over d. And we can solve for x by moving L up here. And then you have the formula exactly right here. X equals lambda L over d. So you might be wondering, how can I tell that these two triangles are similar triangles? Okay, I've done some calculations on paper myself to verify or prove why these are similar triangles, and now I will hopefully convince you. Essentially, I need to zoom in and say that this right here is a vertical line, and this right here is a vertical line. And so this angle right here and this angle right here are alternate interior angles, and so those two must be equal. And so if you look at this triangle right here, it's got a right angle here and this angle here. This one right here, this triangle, this larger triangle, has a right angle here and this angle here. So the other angle left over, which is this one here, and then in this little triangle looks like this, where this side is lambda, this side is d. Here's the right angle, here's the alternate interior angle, and then here's the angle theta. So this one here has the angle theta, and this big one here has the angle theta right there, which is right here. And it requires all three of these lines to be essentially on top of each other, or the same line, which is the case if this distance L is much bigger than this distance x. So I'm happy to show you more in class if this doesn't make sense, but hopefully these two approximations are acceptable to you, and you can see the geometry leads us to similar triangles, and the similar triangles leads us to x over L equaling lambda over d, which leads us to this final equation here. And this equation finds the bright spots. So it's very important that it's finding the bright spots, and then to get the next bright spot, in each further one after that, you can just put in 2x, or you can put in 3x, or 4x, or 5x, or 6x, etc., and that will allow you to calculate the other bright spots as well. So they'll be in equal increments is what I'm trying to say. So like the first one is, say the first one is 10 centimeters, then the next one will be 20, and then 30, and then 40, and then 50, etc. But you can't go too far because this distance x has to stay small compared to the distance L. So if L is like a couple of meters, then x shouldn't go more than 10 or 20 centimeters before the approximation breaks down. Okay, let's do an example problem. Yellow-orange light of wavelength 596 nanometers is aimed at two slits separated by 19 nanometers. What is the distance from the central band to the first order bright spot if the screen is 0.6 meters away? So I like to draw a little sketch here just to help me self-visualize. What is the distance from the central band, that's right here, to the first order bright spot, that's right here. So that's our distance x. We've got the screen L equals 0.6 meters. The distance between the slots is 19 nanometers, and the wavelength of light, I'll put that over here, 596 nanometers. Okay, so we can use our formula. X equals, let's check what is our formula. X equals lambda L over D, lambda L over D, and then we can plug in our numbers. Lambda is 596 nanometers. L is 0.6 meters, and this is 19 nanometers. Notice I didn't have to convert nanometers because they cancel out. Cancel, cancel. And so x equals, we can type this into our calculators, 596 times 0.6 divided by 19. It looks to me to be 18.8. 18.8 meters. Okay, and clearly that is not right because x is supposed to be a lot smaller than L. And so clearly I must have done something wrong either with one of the formulas or with the calculation. So let me check the formula real quick. Lambda L over D. Okay. That is correct, I think. Is that what I derived? X equals lambda L over D. X is lambda 596 nanometers. I think I know what's the problem. I got this problem out of the book, and let me check the value of the separation distance. The distance between the two slits, 19 nanometers, seems much, much too small. Yes, okay. It's not 19 nanometers. I apologize sincerely. This is 19 micrometers. 19 micrometers. So 19 micrometers. And if you know, a micrometer, there's 1,000 nanometers in a micrometer. And so this number we just got here is 1,000 times too big. So we can divide it by 1,000 and we can get 0.0188 meters. And we put it in centimeters since that'll look a little prettier. 1.88 centimeters. So I sincerely apologize if I wasted an extra minute of your time there. But hopefully that illustrates, I promise I didn't do it on purpose, but it does illustrate that if you get an answer out that you know is unreasonable, to go back and check your formula, go back and check your numbers that you're plugging in, and see if you can make sense of why it didn't work. Okay, so the distance up here to the first bright spot is around 2 centimeters, which is significantly less than 0.6 meters, which is 60 centimeters. And so, you know, you can be convinced, okay, now it's a lot more reasonable. Okay, a next topic that we're going to look at is called thin film interference. This is another way in which two different light beams can cross each other's path and then interfere, creating either bright spots or dark spots. So in this case, what you're interfering off is a thin film on top of something else. So some examples are like on your glasses you can get anti-reflective coating. That's a thin film. Sometimes when you look into a mirror, you can see a double reflection of whatever object you had in there. This is a thin film because you've got the actual metallic surface that's the mirror, like say polished aluminum or something like that, and then you've got a thick piece of glass. So the light, when it hits it, some of it is reflecting off of the front of the surface of the glass, and some is reflecting off of the back surface of the glass, which is the aluminum foil or whatever it is. Another example is if you ever look at microscope slides that are pressed together, there's a thin layer of water inside, and a lot of times you'll get some cool looking patterns like this. So the way that this works is the light wave comes in, and some of it bounces off the first surface, but some of it goes through, bounces back off the second surface, and comes out. and then you've got these two waves both coming out, and they can interfere with each other either constructively or destructively. Notice, I'll just reiterate, notice that these are bending when they go through and then bending again when they come out this side. That's because of refraction, of course. But when they reflect off, the angle in and the angle out are equal for Snell's law of refraction, and then just angle in equals angle out for reflection. Cool. Now we're going to do a little bit of math, try to understand this phenomenon. It's a bit trickier than you might think, though, because of two important factors. The first factor is when light reflects off of a higher n value material, n, remember, is the index of refraction. When there's a higher value for the index of refraction, the wave inverts. So say you've got a surface, and here it's like n equals 1, and here it's like n equals 1.3, say, for example. When light reflects off of a higher n value, it inverts. So if you have a wave that bounces in and then bounces out, this wave right here, it adds 1/2 of whatever the wavelength was. So this will now be out of phase with this. Now, of course, these two won't interfere because one of them is coming in and one of them is coming out. But if you had another layer down here and then say it was n equals 1 again, then the part that went through and it bounced back here, right here, there would be no change because you're going from 1.3 down to 1. So again, it just happens when you're going from a lower index into a higher index, then the wave will invert. So basically, instead of going like this, it switches to going like this, which is the same mathematically as adding 1/2 of a wavelength. Okay. The second thing is the wavelength inside the thin film is changed. So if you've got a thin film, when the light is coming in, it has a certain wavelength. But when it comes through the material, it's got the wavelength in the film. And the wavelength in the film is actually going to be different than the wavelength outside because you learned that when light travels into a medium, it changes speed and therefore changes wavelength. And now, I guess I should modify this and say, instead of vacuum, I'll say whatever is outside. Because the light doesn't always have to be coming from a vacuum into the film. It might be coming from water into glass or something like that. So you've got the wavelength on the outside, and then you've got the wavelength in the film, and that's going to be different. So then it's going to bounce back. So the light travels both in and out. So whatever the distance or the thickness of the film is, the light travels twice that distance inside of the film, and so you have to find the wavelength of the light inside of the film and then get the distance and double it, and that's how you can tell how much distance it traveled and how many wavelengths it got offset by. So if you want to get bright spots on the outside so that this one coming out and this one coming out, these two coming out, are in phase, then the total offset should be 1 wavelength or 2 or 3, a whole number of wavelengths. So you might pick up 1/2 or a whole wavelength from the reflection off the surfaces, and you might also pick up 1/2 or a whole wavelength from this extra distance traveled inside of the thin film. So you can imagine a wave is going along like this, and it has a certain wavelength. So if the thickness of the film is like, like that or something, on the way in, it picks up 1/2 a wavelength, and then on the way out, it picks up another 1/2 of the wavelength. Or maybe the surface of the film, the thickness of the film is only 1/4 of a wavelength. Then it picks up 1/4 on the way in and 1/4 on the way out. So as the wave travels through the thin film, it's going to pick up some portion of a wavelength, or maybe more than one wavelength. Lastly, to get a dark spot, the total phase change needs to be off by 1/2 number of wavelengths, so that on the way in, maybe it's coming out at an even number of wavelengths, and after bouncing through the film and coming back, it's now like 3.5, and this is 3. Then they're off out of sync by exactly 1/2 a wavelength. The max of one will meet the min of another, and they'll cancel out. Okay, so to do these kind of problems, it's critical that you draw a picture, then you label whether or not there's an inversion, which will give you 1/2 a wavelength shift. Then you find and label the wavelength inside the film, and then you set up your equation to decide, how many wavelengths off you need it to be, and then you can solve for the variable that you want. So these are probably one of the trickier types of problems that you'll have to do in this chapter. Let's do an example. What is the thinnest soap film, n equals 1.33, for which light of wavelength 521 will constructively interfere with itself? So let's draw our diagram here. So let's say the light is hitting a soap film from air. So n equals 1 for air, then it's 1.33 for the soap, and then it's 1 again for the air inside the soap bubble. So you've got one light wave coming off here, and then you've got the other one coming off here. So right here, you're going from 1 to 1.3, you're going to get an inversion. So you're going to get plus 1/2 on this one. And then right here, this is going from 1.3 into 1, so there's no inversion here. So if you want these two guys to be in phase, this guy also needs to get plus 1/2 wavelength. I hope that, that seems like it should make sense. So the first one coming off gains a 1/2 wavelength from the inversion, and this one, it needs to gain a 1/2 wavelength to be in phase so that it will constructively interfere. That means in phase. So that means that as it travels from here to here and then back out again, that needs to gain, that's where it needs to gain the 1/2 wavelength. So if it goes in and then it comes back out, it should gain, I don't even have to set up an equation for this really, to be honest. It should gain 1/4 of a wavelength each way, on the way in and then on the way out. So plus 1/4 right there, and then plus 1/4 right there. So the total of those two gives us the plus 1/2. Okay, so the thickness of this material, should equal 1/4 of the wavelength. And the question is, what is the thinnest soap film for which the wave will constructively interfere? So that's going to be 1/4 of whatever 521 is, nanometers. And so the thickness of the material, 1/4 of 500 is 125, 1/4 of 20 is 5, right? So 130.25 nanometers. And so sometimes you need to set up an equation, but sometimes you can just see the kind of answer almost pop out at you once you try to make these two match up. Since they need to constructively interfere, they should both be at the same level. If it would have said they want to destructively interfere, then you just want these guys to be off by 1/2 wavelength, in which case this one's already off by 1/2 wavelength, so the thinnest it could be is technically 0, but if it's 0, then it's not really there, which means if this one was 1/2 and you wanted this one, it couldn't be 0, so the next way it could be off by a factor of 1/2 is to go up to 1. Then you'd have to pick up 1/2 wavelength in, 1/2 wavelength out. So essentially, if we double the thickness of this, then it will be destructive interference, etc. So hopefully that's a good example, but I'm happy to do lots more in class. All right, take a break. I know both of those topics have been pretty mathematical. It requires a little bit of involvement to understand the ideas, so please take a break.